very excited to talk to you about deep learning with Anaconda. One, because this is becoming a very interesting topic and I'm getting a lot of questions about it. So while we may not have time for questions here, I am at the demo kiosk showing off the example I'll be showing you here, and we can come chat about it. So what is deep learning? Many of you may have heard of deep learning. Have you ever heard of deep learning before you walked in here? Okay, yeah. They've done an excellent marketing job getting that name into your brain. Deep learning is the return of neural networks. Neural networks have been around a long time. Maybe they were called perceptrons or other things. And they had kind of a PR problem where they didn't achieve their promise early on in their life, doing all of the amazing things that our brains do. But thanks to a number of developments that I'll talk about, neural networks have come back and become very popular for certain kinds of, you've seen a lot of high-profile successes. So you've seen some amazing things with image recognition, automatic captioning of images, automatic language translation between English to Chinese and all sorts of things. Speech recognition, all sorts of things are now becoming possible using neural network technology. And so a lot of people are asking themselves, well, how do I get started? How do I get into it? And I'll tell you a little bit about how Anaconda is a great way to get started. So what happened? Why did neural networks go out of fad and then come back in suddenly? And it's really, I think it's the convergence of four key factors. One is faster and specialized hardware. Moore's law and then sometimes sort of above Moore's law levels of development, allowing people to just get faster CPUs, more CPU cores. GPUs have been huge in this, specialized processors that were not invented for deep learning, but happened to accidentally be good at it. And then now there's a lot of investment going into deliberately making them better for deep learning now, once that was realized. So you have the hardware piece. The data piece, much bigger training sets. One thing I'll mention is that neural networks, especially large complicated ones, really need a lot of data to train. And so until you're at a stage where you have enough training data to train one of these, it doesn't matter how much CPU you can throw at the problem or how much GPU you can throw at the problem. The other thing is improved algorithms. There's been an immense amount of research over the years in how to, what kinds of neural networks work for different sorts of problems, how to train them efficiently, what sorts of optimization algorithms to use when you're doing training. So that basic fundamental research has really been a huge deal. And then finally is open source tools. All of the technology, a lot of the real active work in deep learning is all being open source now. So any researcher anywhere can pick this up and start experimenting with it, which is really exciting. And this feeds back into the loop of getting more data, getting better tools, all of that stuff. And then the adoption is feeding into hardware development. So this is pretty amazing. So what is a neural network? And the danger of this name is it's a little bit loaded. You think about it and you start making the biology analogy for you. You're like, I've got a brain inside my computer and I feed it data and out comes inferences or something. And the neural network, the name is suggesting that it's a sort of biologically inspired in the sense that it's a connection of very simple computational units, in a large mesh, but not an arbitrary mesh, a mesh with a particular structure, which is where it differs, I think, from the biological case. It's very flexible, so with a couple of basic concepts repeated a lot, you can handle many different problems from audio processing to time series prediction to image processing. And it's trainable. It would be very easy to make a giant complicated model that you actually couldn't train effectively. And so by structuring the model in a certain way, it allows you to be able to feed all of that training data that you now have sitting on your disk. And, there we are. And, train it out. So at its heart, a neural network involves a node. And there are actually many kinds of nodes. There's not just one node, but it could be something as simple as sum up a bunch of numbers, I left off the weights, and add an offset. It could be that very simple, almost linear algebra feeling kind of operation. But then you take that node and you replicate it into many nodes into a layer. And this is really the heart of the neural network, is that it's organized into layers. And those layers take data, they don't depend on each other. So this is where the parallelism comes in. I don't have that. This node doesn't depend, the top node doesn't depend on what the bottom node is doing. But then you can take those layers and connect them up into a network where each layer depends on the one before it. And this seems not that exciting, but it actually is this structure that has led to a tremendous amount of innovation, because just as the network is layered and there are sort of standard patterns people follow building these nodes, it lets you actually divide up the problem that you're trying to solve, a very hard problem, into different layers of abstraction. And so this is I think this sorting of the problem into starting with hardware, making multi-core CPUs, many-core CPUs, GPUs, all of those things. Advances there then feed into primitives, specific deep learning, fundamental primitives where you as a researcher are not going to be calling cuDNN directly. But the software you're using will be using cuDNN, and you are relying on the experts at NVIDIA to have made those primitives work as well as possible on their hardware. And there's many of these. Intel MKL has added support for DNNs. AMD recently announced MI Open. All of these sort of sit at this layer. And then above that is tensor math, which if you're not into math, you may be looking at a tensor and wondering what a tensor is. You don't need to know necessarily, but it's really about the sort of fundamental mathematical underpinnings of a neural network and many other machine learning algorithms as it happens. And so things like TensorFlow and Theano and PyTorch, and actually, this keeps going off. This slide would have been 4 times wider if I'd listed them all. Those operate at a layer that you can use them for deep learning, you can use them for other things. And then on top of that, there is a high-level abstraction that is really just focused on neural networks. And these boundaries are not totally rigid, and the lines are not, people blur the abstractions a little bit. But things like Caffe and Keras and TF-Learn are really designed to get so that you can define a neural network and train it with a minimal amount of code. So in Anaconda, this is becoming a new direction for us to focus Anaconda's work. We have really well-established tools in ETL and DataFrames and scikit-learn for all of the traditional machine learning stuff, but deep learning we're getting more interest and more questions. So today, you can install Theano, and you can install TensorFlow, and very soon we will have GPU-accelerated TensorFlow and possibly other things. So all of those are coming very soon, and actually I would encourage you, if you have a wish list, come find me at the booth. I'm collecting information and feedback from people about what sorts of projects they'd like to see. So the great thing about doing deep learning in Python is you can leverage tools like the Jupyter Notebook. So the Jupyter Notebook gives you a natural place to do your experiments, your training, to see results. I'll have a demo at the demo station that will let you look at and see what one of these models looks like. And here I've shown you a snippet running in Anaconda Enterprise Notebooks of the Python code that defines the layer. So you don't have to necessarily understand this, but each line of code effectively corresponds to one of those layers in that network. And so there's a very natural way to think about and program your neural network without having to do a whole bunch of extraneous typing. And so you can take this model. This is actually a fairly simple model for doing digit recognition. So there's a famous data set of handwritten digits, and then the classification of those to actual, was it a 5 or a 0 or whatever. And you can imagine this comes up all over the place. People handwrite zip codes on notebooks, and you would like a machine that can auto-sort letters by what zip code they go to. And so this is a classic image recognition problem that's fairly compact, and that network I was just showing you, which has maybe 5 or 6 layers in it, can train in about 4 minutes to 98% accuracy. That's actually, not that good. One person stopped by the booth yesterday and pointed out that he had built a model that basically hit 100% on this. And so the goal here is not to classify digits. It's mostly to show you an example. But this is 4 minutes on a GPU. This would have been 10 times longer with an 8-core CPU. And so this is a huge win for researchers who are wanting to experiment, because a real key feature of neural networks is you have to experiment. There are no first principles right answers to solve these problems. You really have to try different things. And one part of experimentation is assessing your failures. So you might do this, and in the same notebook, you'd be like, okay, I had 2% wrong. What are examples? Am I seeing a pattern here in how misclassification is occurring? And so here are some examples of some digits that this network had a problem with. For some reason, it seems 6s and 0s are really confusing. It doesn't seem to key off of that extra tail at the top, and then a partially written 8, various things like that. So you get some insight into what is the model struggling with and what isn't, and that might, with some intuition, feed back into, okay, maybe how I should restructure my model. So just to conclude here and hand some time over to Matt, now is a great time to experiment with deep learning. Python is a great language for prototyping, and you can do deep learning in Python. You can create and run your training experiments in the Jupyter Notebook, which gives you a record of what you did. You can share it with your colleagues. It's a great way to exchange data. It lets you visualize the results right there. Again, it's code and text and data and pictures all sort of intermingled. And there are more deep learning packages coming, and please communicate with us what you want to see. We want to bring the best out there to you in Anaconda. So please let us know what it is you want to see, and we'll fold that all into our roadmap. So, all right.
Thank you, Stan. Okay, so this talk was really designed to be sort of a half TensorFlow talk and a half Dask talk. Last weekend, or this weekend, I got sort of ambitious and decided to see how well I could make them play well together, hence sort of the fun bit. So what I'm going to do is I'm going to do sort of a 10-minute talk, sort of generic Dask, not deep learning focused. There'll be sort of a 5-minute talk after that about how to use them together as sort of an experiment. And it'll show that it's relatively easy, both because TensorFlow is well thought out and because Dask is relatively flexible. But let's talk about that a little bit. It'll sort of be a combination of slides and demos. My name is Matt. I work in a library called Dask. Dask is a library to parallelize Python code. Most people first see Dask through Dask DataFrame, Dask Array, or sort of some machine learning stuff. And those are parallel variants of NumPy or Pandas or working with scikit-learn. So Dask provides a large parallel array or a large parallel data frame that can work on many cores on your laptop, working off of disk, or on many machines in a cluster. What we found generally, and those follow the NumPy and Pandas APIs, those use NumPy and Pandas on the hood, so they're very familiar to people, they're very fast. What we found interacting with both with companies and with academics is that a lot of parallel computing problems didn't easily fit into arrays or data frame problems. You all do very weird things, it turns out. And it is sort of awkward to shove it into a big data frame. And so what we found is that while Dask DataFrame and Dask Array weren't appropriate for all situations, the underlying system, just Dask core, was appropriate. And so that'll be sort of a theme. That lower level piece is also what we're going to be using when we launch TensorFlow in a distributed cluster in a nice way. So very briefly, let's talk about sort of the easy to understand, sort of sexier things. So we'll move down to less sexy, but I think more fun things. So a Dask array is a logical collection of many NumPy arrays, either on your hard drive, on your laptop, or in memory on many machines in a cluster. Similarly, Dask DataFrame is a collection of many Pandas data frames. So maybe I have a cluster with 100 machines. There's 1,000 Pandas data frames and all the memory everywhere. And Dask DataFrame is just coordinating all of those Pandas data frames for me. So as an example, let's align things a bit here. So I have the New York City taxicab data set on a...
It's not showing up on the screen.
Ah, it's not showing up on the screen. That is unfortunate. AV in the back. I'm showing something on my screen that is not on that screen.
I think that's a...
Okay.
There we go.
Was this slide showing when I was talking earlier? Okay, great. Thank you. Aha. So I have a bunch of CSV files on S3. This is a New York City taxicab data set. It's a bunch of CSV data. It doesn't fit in RAM. I would love to use Pandas with this data set, because maybe I like Pandas, maybe I like its speed, I like its sort of flexibility. Maybe I employ a lot of data scientists who are already pretty well trained with Pandas. And I can read a little bit of this data with Pandas, right? I can read sort of 5 rows of data or some small subset. And so this data set has every cab ride in New York City for the year 2015, showing when it happened, how many passengers there were, breakdown of the fare, how much was the tip, et cetera. But I can't fit all the data in RAM in one machine. So now I have sort of stuck. Which of the various solutions do I use? So what I'm going to do is I'm going to connect to a cluster. And that cluster has 10 machines on it. Each machine has 8 cores. And I'm going to load that data, instead of with Pandas, I'm going to use the Dask DataFrame function, read CSV function. And you'll notice that this function looks a lot like the Pandas function. It's got keywords like parse dates. It's taking, instead of a single file name, sort of a glob string of file names. What we're seeing here on the right is we're seeing as our many sort of 80 cores on our cluster are pulling blocks of bytes from those S3 CSV files, then calling just sort of the normal vanilla Pandas read CSV function on those bytes. And they're then producing 300-ish pandas data frames in memory across my 10 machines. So I've got these 10 physical machines on some cluster somewhere, and we're sort of populating those machines with pandas data frames. Okay. What we get back is not a pandas data frame, but a Dask data frame. And this object is a logical collection of all those pandas data frames. And this object, it'll sort of coordinate to all my pandas data frames what to do. Dask here is not doing the computation, pandas is doing the computation, and Dask is just a very effective secretary. It's just coordinating all of our machines in the cluster. But it still looks and feels, it sort of creates that illusion that you're still playing with just pandas. So for example, here we go to the head of a data set, we can compute the length. And what Dask did when we computed the length, let's zoom in here a little bit, is it computed the length of all of those pandas data frames, and those computations took, a couple hundred microseconds, a dozen microseconds. And then it communicated all those intermediate results, that's this red bit here, to one machine, and then it summed those results. This is a very simple computation. We can do something more complex. Let's say we'll do maybe a complex group by operation. And here, if you're familiar with pandas, this should look familiar to you. You should be pretty happy. But it's thousands of little computations. We get back to the nice result that New Yorkers tip fairly well, especially at 4 a.m. in the morning. Okay. But again, this was sort of useful if you have big data frame problems, and not everyone has those problems. Here's a simple problem you might have. Here's some Python code that clearly has potential for parallel computing. There's some for loops in here. Based on the data, we're using one function or the other, but it's not clear exactly how to convert this into a data frame or into an array. That process is awkward. And so instead, we can just use other APIs built on top of Dask that allow us to do sort of arbitrary parallel computing. So at its core, Dask is a dynamic distributed task scheduler. It can sort of just run arbitrary computations that are dependent on each other. It looks something more like Airflow or Luigi, if you're familiar with those projects, but it operates at sort of a scale and a performance of something more closer to Spark. So sort of the flexibility of some of these more data engineering projects, but the scaling and data management of something more big data-y. Okay, Dask, the task scheduler, here's a machine learning problem. We compute graphs like this, where every circle is some Python function that needs to run somewhere on my cluster, and Dask will figure out where to run that for us. Dask cluster is made of one centralized scheduler with many workers, and that scheduler is sort of coordinating all the workers, but the workers will communicate peer-to-peer with each other. We can have many clients, that's us, on our notebooks and our scripts, in something in a data engineering pipeline somewhere that's submitting computations to this scheduler. Maybe multiple of those. Okay, so briefly, I'm going to keep some time for the TensorFlow stuff. Dask parallelizes Python across a cluster, or on a single machine. We spent our first year of development just parallelizing single machines or large workstations. We found this to be very productive environments. But we also support sort of custom workflows, and that honestly has been where many people are very excited about the data frames, and that's very useful if you have a lot of maybe time series data. But there's a lot more interest, at least sort of in enterprises that I've been interacting with, about this ability to schedule arbitrary task graphs. That is something that has not been around before and is of high value to many people, both inside of companies, inside of academia, et cetera. I showed only sort of simple things here. I want to show one more small example. So here, rather than deal with large data frames, I have these small Python functions here that I want to call on my cluster. So I'm writing my own code. It's not data frame stuff. It's my own custom stuff. I have my own objects. And I'm going to use a different API. There's a concurrent futures API inside of Dask. So I submit some task. It runs. And I get back sort of a token or a pointer pointing to wherever that task ran. And I can run that inside of for loops. I can link tasks together. And I can write fairly generic Python code that actually runs nicely on my cluster. So the code here on the left might look like something more similar to what you do internally that isn't a big data frame. I can write more complex computations. Here's a tree reduction written in a few lines of normal Python code. Not that you should get this immediately, but hopefully it's not too scary. And we get a nice computation. And Dask handles all the workers going up and down. It handles load balancing. It handles a lot of stuff that I don't want to think about. But it still gives me the freedom to design clever algorithms. It gives me the freedom to schedule certain tasks on certain kinds of machines. There's a lot of flexibility here. And that flexibility is going to become very important when we start talking about TensorFlow, or generally speaking, how does Dask interact with other distributed systems? So TensorFlow is just sort of one example. OK. Again, this is not intentionally supposed to be a Dask and TensorFlow talk. We sort of merged it. I was sort of playing around last weekend. Spoke to a friend of mine, Seven Hoyer, who works both on Dask and TensorFlow, and he sort of had some ideas going back and forth of how this interaction could occur. So I'll talk a little bit about how it might occur in theory, and then we'll sort of show an example of it running. So TensorFlow is often used in a single machine, so too is Dask. There can both also be run on a cluster. So you might ask the question, where does one sort of leave off and where does the other one take on? TensorFlow is focused on deep learning, or generally speaking, on computational intensive array computing. Dask is more general purpose. Dask isn't really specialized to anything. It sort of tries to do all things moderately well. And so you can use Dask for things like data ingestion and also to stand up TensorFlow and then to sort of coordinate those actions. So Dask is, again, a much better secretary, and TensorFlow is sort of like a Ferrari just for doing deep learning stuff. We sort of want both. So some things you could do relatively simple things, like hyperparameter searches, or sort of scaling one model to predict on lots of data. These are relatively simple. Any system can do this. Spark can do this. Flink can do this. Hadoop can do this. It's relatively simple to do. What's sort of more challenging, more interesting example to play with is distributed learning. So what we're going to do is we're going to deploy TensorFlow using Dask. This tends to be a pain point for the community, the TensorFlow community. And then we're going to do some pre-processing in Dask and then give that to a complex TensorFlow training system. So let's skip that. So here's a more interesting TensorFlow workflow on a distributed machine. I have, so my model is going to fit in memory, but I have too much data to fit in memory. Additionally, I want to spread out my training on many different workers to sort of make it go faster. So on the top here, I've got 5 TensorFlow workers, and they're going to be doing some training. And they're going to be fed NumPy arrays or pandas DataFrames from something. There's no sort of obvious way of how to get them that data. And Dask is going to serve that purpose. It's going to give them that data. Additionally, with TensorFlow, I'm going to have a couple of parameter servers. These are going to be sort of synchronization points within TensorFlow. Again, this is all the TensorFlow stuff. I'm sort of describing how TensorFlow works, not how Dask works. There's also just one way of using TensorFlow. So there's just a common pattern that exists. And also have a sort of a final scorer. It's going to be watching those parameters, and every second it's going to be saying, okay, we're doing this well, we're doing this well, we're classifying this well. It's going to be feeding that information to the rest of the network. That'll be serve as a stopping criterion. So there are a few problems. One is, how do we set this up? How do we give it a cluster, set up all these workers, connect them to each other, and then tell all the different TensorFlow servers what they should be working on? And then second, how do we feed data to it? So we can use Dask to deploy a TensorFlow model, a TensorFlow cluster. I wrote a function, this start TensorFlow function, I think Sunday afternoon. It's about this long. This is the amount of code I had to write in order to bootstrap TensorFlow. You shouldn't necessarily look at this and try to understand it, but you should appreciate that it is 40 lines long. So this is the amount of code we had to do in order to make it easy to bootstrap TensorFlow on Dask. And this is, again, a testament to both how simple TensorFlow is and how flexible Dask is. Secondly, we're going to load our data using Dask DataFrames, Dask arrays. And we're going to feed that data into TensorFlow. So what we're going to do is we're going to, on all of our Dask workers, we're going to locate a TensorFlow worker, and Dask will set that up for us. And there will be a queue along which we'll just send NumPy arrays. So Dask workers can collect data, and they can just shove that data into that queue, and then TensorFlow can take over from there. So we're going to have 2 different distributed systems running side by side, but living in the same space, living in the same Python process. And it's very easy for them to interact, because they're just interacting through Python. There's sort of a nice lingua franca. They're moving NumPy arrays around. It's sort of very friendly. So let's play with that. Also, you're not expected to understand all of this. This is a sort of advanced TensorFlow situation, kind of an advanced Dask situation. The point I want to get across is that you can do wacky things, and that wackiness is available to you. So I have my cluster. I'm going to sort of clean off the old work. And I'm going to gather the MNIST data set, the same data set that Sam was working with before, but I'm going to sort of expand it artificially a few times to make it less convenient to work with. And so the Dask workers are going to go out, they're going to compute that data for us, and we can go and look at that data set. So this is now just a large distributed NumPy array across my cluster. And I can easily go look at one particular image. I can look at another image. I can do things like compute the mean of these images. They're sort of fuzzed out, compute the variance. Ask for data preprocessing, which is a really important step for any sort of machine learning pipeline. I'm going to sort of set things up to batches. TensorFlow sort of likes things in a certain size. And then I'm going to start TensorFlow. So I don't have any TensorFlow running right now. And now I have a TensorFlow cluster running. And what we have is that we actually have those same sort of classes of work we've talked about before running on the same machines. So you'll notice that the parameter server, this PS group, is running on this machine 106, and that's running on port 2222 for TensorFlow. And that same process, that same machine, is also running with Dask on the same process. So they're now sort of cohabitating the same processes. They can talk to each other, they can share data back and forth. I'm going to sort of copy an example from the TensorFlow documentation, which is long. I'm going to set up some roles for our different workers. And I'm not going to do this much, but we can go ahead and start those tasks. These are long-running tasks. They're just, so we can see here, there's a scoring task, there's a few TensorFlow tasks. They're just running all the time. They're just sort of waiting for stuff to happen to them. And they're listening. So Dask has set these up, and we're going to go ahead and then feed data into them. So again, the goal here isn't for everyone to understand what's going on here, but the goal is to understand that it's easy to set things up together. It's easy for them to play well together. Getting a 3-minute warning. So that's no point. So some final thoughts. First of all, the network I just did, the example I just did, works way worse than Stan's example. Stan's example runs on a single machine, but it uses a more clever algorithm, and that's probably a better place to start. Distributed anything is probably not often worth it, unless you really need it. Two systems work well together. Dask can provide things like setup and orchestration, while TensorFlow can provide a lot of the algorithms that are sort of culturally fit for that community. And this demo was the work of a long afternoon. This was not like a collaborative effort taking many weeks. And so even if you're not into deep learning, this may be a good example of what you can achieve with some of these projects using Anaconda generally as a flexible platform. OK, and that's it. We have a couple minutes for questions. 1 minute for questions.
For one quick question. Does anybody have a question for either Matt or Stan? All right, just be sure to speak into the microphone that's...
Yeah, so the question is, when would I use Dask versus Spark? They're both great projects. Generally speaking, Spark will be better if you, a few answers. One, Spark is one conglomerate project. So if you want to install one thing and have it just work, Spark is probably a better choice. Dask is a component of Anaconda. So it works well with pandas, it works well with NumPy, it works well with scikit-learn, it works well with TensorFlow. So there's a sort of this a la carte choice, or this give me everything in one package choice. Spark is everything, Dask is component. Spark will certainly be better at things like business analytics with SQL. Spark implements SQL, Dask doesn't. Dask tends to be better for more flexible situations where your computations are maybe more complex and are easy to write down with Spark. Dask is a project, so if you're using Python code, it's much more friendly in that sense. If you use a lot of Java work, Spark might be a better choice.